Hey guys, welcome to Digital Srini channel on YouTube. And if you haven't already done so, please go ahead and hit the subscribe button right now because I know you love this channel. Okay, this is a continuation of our discussion from the last video where we started talking about semantic segmentation of BraTS2020 dataset. In the last video, we looked at a high level what the data looks like and what the plan is. And if you haven't watched that, I definitely recommend you watching that video so you know exactly what the plan is for this video and the next couple of videos on this topic. Okay, today we are going to talk about getting the data ready, like where to download the data from, and once you download the data, what you do with that data, how you can chop the volumes into smaller volumes and all that stuff. So after this discussion, you should have the data ready to be trained upon. Okay, so that's the whole point of this video. Now, just to give you a quick idea on what we're talking about, in case you haven't watched the previous video, we looked at what BraTS dataset is, right? You can go ahead, go to this link, go ahead and download this. Beware that this is 40 gigabytes. And this dataset is a multimodal dataset with multiple NII files. And multiple, when I say that, you have 4 different modes of images for the same volume. Okay, for the same volume that represents the brain, you have 4 different images or 4 different volumes. Okay, with slightly different representation of the same data, I should say. So T1 stands for the native image, native file, and then the T1 weighted is contrast weighted. As you can see, it seems to be some sort of a contrast enhanced image right there, and T2 weighted, and then FLAIR volumes, right? So these 4. So these are the 4 volumes, and this is the segmented volume. And the segmented volume represents 4 different regions. Label 0 is unlabeled, meaning bulk of the volume is label 0. And then you have label 1, 2, and 4. 3 is missing. There is nothing with a value of 3, which means we have to reassign value of 4 to 3. Okay, just so you have a continuity between 0, 1, 2, and 3. And also, the other thing that we're going to do right now is not use T1 image, but use T1 CE, FLAIR, and T2. By the way, I looked at some of the code that out there on this topic of BraTS. They're only using like one channel, whether it is FLAIR or T1 CE or T2. I think there is rich information when you combine multiple of these. You can combine all 4 into one volume, but I don't see a good benefit of including T1, especially after seeing the mask, right? I mean, the features that you see in the mask are clearly visible in T1 CE, sometimes in FLAIR, and also in T2. So why not just use these 3 volumes and ignore T1? Okay, that's our idea right now. Okay, so with that information, let's jump in. And first, let me start by showing you the page where you can download this. Okay, so here is where I got my data. Okay, and I'm providing you the link, and if not, go ahead and Google search for BraTS2020 dataset training plus validation, because I guess I'm not sure if the original 2020 BraTS dataset from wherever that university link is, if the data got divided into training and validation, but here you can download them pre-separated. Not a big deal. Just get your hands onto this dataset. That's the key part. Okay. And also, while we are here, let me show you the Unlabeled library. The way you install that is just pip install NIBABEL, and that gives you the ability to read the NII files that the BraTS dataset contains all the images in the NII file format. Okay. So once you're done with that, now let's go ahead and open the folder. And when you download this, when you download the dataset, it's in a zipped format. Again, use WinZip or WinRAR. I like WINRAR, WinRAR package, because it can work with .gz, a few other compressed file folders. So I've used that to unpack the material, and I got BraTS2020 training and validation. Let's go into training data. So in here, these are all the ones that I kind of created, but what you will see is this one, right? MICCAI BraTS2020 training data. So if you go in there, you will see 371 items. Of those, 369 will be the folders and the 2 CSV files. We're going to ignore the CSV files for our task. But these 369 folders, each of these, let's open this. You see it has a FLAIR image, a segmented mask, T1, T1CE, and T2 images. Okay, and all the names, they are pretty appropriate. You know, BraTS2020 training with the folder name. Okay, so that's the volume name. Except for the one in 355, the seg has some weird name. Go ahead and fix it. Okay, meaning rename that folder, that file, to match rest of these files. That way it makes it easy for us to read all these images at once. That's the only thing you need to do. Otherwise, these are all pretty much like you see. You have these individual NII images. So the first thing we'll do is get a good understanding of what's going on, and then go ahead and process these images in a minute. Okay, so there we are. Now let's jump back into the code and see what the plan is. Okay, so first of all, pip install the Unlabeled. So once you're done, you can import that. Okay, here I'm importing that as NIB. So I'm importing NumPy, Unlabeled, glob, and obviously to categorical to convert. This is a multi-class or multi-class semantic segmentation. So you need to convert your images or the volumes into categorical. Okay, so that's what that does. And something for plotting, something to save if you want to save them as TIFF files. TIFF file is a great library. And from scikit-learn, I'm going to use min-max scaler to scale all the values. Okay, so this is the plan. So let's run these lines. I just restarted the kernel, so it should take a second for it to load the TensorFlow. And again, I'm using as of May, June 2021, end of June, July, whatever the latest TensorFlow is. In fact, let's go ahead and import TensorFlow as TF. Okay, I just want to make sure you guys have a similar version as I do. TF. So I'm using 2.4.1. Okay, so in case you wonder. Okay, there you go. And the next step is just understanding the data. So first of all, let's set our training dataset path. Our training dataset is BraTS training, and that's my training folder, right? So I set the folder path. Next thing is I'm going to load a single image. Which image am I loading? The number 355, single image. Okay, and the way you load that is nib.load and give the path of the image, and at the end get fdata. This the entire thing is going to load this NII file as a NumPy array. So let's go ahead and run it. Okay, so when we do that, you see I have 240 by 240 by 155. Okay, that's the FLAIR image size. And these are all floating point numbers, but that doesn't mean they're between 0 and 1. In fact, let's go ahead and print out the maximum value right there. You see the maximum pixel value is 1854.6. That gives us, a good idea that we need to rescale these using min-max scaler or whatever the scaler that you choose to use. Okay, so that's why the next step I'm trying to do here is, remember we defined our scaler as min-max scaler up here. I'm going to apply that to my image right here. Okay, I'm going to apply scaler fit transform. And what am I doing in here? Reshaping it a couple of times. Go ahead and run that line on a different data set if you want to get a good understanding. What I'm trying to do here is scale it. First of all, to scale it, you cannot just scale it on a 3D volume. You have to convert that into a 1D and then reconvert that back into the 3D. So I'm flattening it and then reforming the 3D volume. That's exactly what that reshaping a couple of times is doing. So I'm fitting right there. So at the end of this, I should basically end up with 240, 240, 155, again, array. Now let's go ahead and print the maximum value right there. You see the maximum value is 1.0. So everything is scaled between 0 to 1. Again, that's what min-max scaler actually does. Well, min-max scaler, you can define what the min and max is. If you don't define it like we did here, the min is 0, max is 1. So my minimum value in this volume is 0, maximum is 1 right now. It's scaled to 1. Let's do exactly the same for all other images. Test T1, all of these. Okay. So all I'm trying to do is load a single image to get a good understanding of how the image looks like. and then converting that into a, not converting, applying a min-max scaler. Okay, that's what we have done so far. Now what's remaining here is the mask. Okay, so for the mask, obviously I'm not going to scale the mask. First, let's load the mask. Okay, so there you go, my test underscore mask, and let's print out the unique values in the mask first. If you do that, you see how the unique values are 0, 1, 2, and 4. Remember, these are the labels. So they're 0, 1, 2, and 4. We want them to be 0, 1, 2, and 3. Okay, we'll get there in a second. First of all, these values are all floating point values. I don't know why, again, but we can convert them back into an unsigned integer 8. So let's go ahead and do that first. Now let's print out the unique values one more time, and you should see 0, 1, 2, 4, and this time this is basically a unsigned integer 8. We don't need all that memory that's required for floating 64 to store 0, 1, 2, 3, right? So that's why I'm converting that into integer. Okay, now in the test mask, wherever the value is 4, change that value to 3. So I'm reassigning 4 to 3. So let's do that, and let's go ahead and print the unique values. Now we should see 0, 1, 2, 3. So all we did is reassign 4 to 3. Okay, again, most of you may think, hey, stop dwelling too much time on the basics, but the viewers of this channel come with diverse skill sets, so sometimes it helps to cover these basics. Okay, so we are trying to understand a single image, and we did all of that to get the image ready. And now let's look at a few planes. Okay, so here I'm randomly, in my image, I'm randomly selecting a slice and printing or plotting my FLAIR image, T1 image, T1CE, T2, and the mask, right? So that's exactly what we are doing right here, just to get a good feel for how these volumes look like. You see, not much information anywhere except for that little thing, and even that is unlabeled. So why use this information, right? So this is the type of information we are looking here. Again, most of the volume is empty except for this little area. Let's do another random plane. Again, no label here, even though you have some data. No label there. The actual labeled parts are very minimal. So let's keep doing this until we find something useful. I'm again randomly plotting some of the, yeah, you have some label right there. Yeah. So I'm randomly plotting some of these planes. There you go. That's a very useful volume, right here if I can crop it. Yeah, right there. Okay, so far we got some understanding. Now let's go ahead and the next part, what I'm trying to do here is, now that we have our test image, FLAIR, T1CE, and everything, let's go ahead and combine that into a single volume. So you have 3 volumes, separate volumes. I want them into single volumes so I can train it, my model later using this 3-channel 3D volume. So that's the idea here. So the way you can do that is np.stack along the axis 3, right? And stack what? Stack my FLAIR image, T1CE, and T2. The order doesn't matter as long as you stick with the same, right? I mean, the order doesn't matter. So I'm going to combine that. And if you look at the variable explorer, my combined X is 240 by 240 by 155 by 3. And this 3, hopefully represents my FLAIR, T1CE, and T2, 3 channels. So this is a 3D volume, multi-channel 3D volume, multi-band 3D volume. Okay, again, I'm going a bit slow just to make sure you're with me here. Okay, now you know that bulk of the outside of these regions are dark, right? Or there's no information at all. So here I'm cropping it. I'm cropping, the top and side a little bit to get a volume of 128 by 128 by 128. You see here we have a volume of 240 by 240 by 155. I'm cropping it so it is 128 by 128 by 128. Makes it easy for us to handle those. Okay, so let's do that for our X and also for the mask. Again, so far we are doing only for one image. Reason, once we do this for one image, we know what's going on and apply that to all the images and save that data. Okay, so that's the plan. Okay, so I did that for test image and test mask. Now, if you look up here, my test image, if I can see, what did I call? Combined X. My combined X is 128, 128, 128 by 3. and my test mask is 128 by 128 by 128. So basically we cropped both of these volumes. Now let's plot exactly the same way that as before, just to make sure everything looks fine. So there you go. Now you should see things a bit bigger because we are cropping them to 120, now you see we are maximizing this volume. That's pretty much it. Okay, so now let's move on, and at this point you can save this. If you want to save this as a TIFF file, use the imsave from the TIFF file right here, TIFF file library, and save it as TIFF, and that can save multi-channel files. But let's go ahead and do that actually. So that can save multi-channel files if you want. So if I go back, combined BraTS training data, so there is the TIFF file right here. And if you try to open this using any image processing, it doesn't make sense unless you open only in Python. In most image processing software, this may look a bit weird. So in my case, I choose to save this as a NumPy array, this data that we just processed, rather than a TIFF file. Because what if I have 4 channels? Then it can be a bit challenging. So NumPy array, no issues. So let me use my np.save or numpy.save and save this as a NumPy array. And let's save it, and we should have that file right there. Yeah, I call it 255, but this is a 355 slice, but it doesn't matter. We are just testing right now. Okay, and now that we saved it, let's go ahead and load the same. Why? Again, I get paranoid whenever I do these things. I want to make sure when I save it, when I load it, it looks exactly the same way. So let's go ahead and load my image right there, combined 255. Now there should be a new one called my image, you see up here, and that's exactly 128 by 128 by 128 by 3. If you are curious, this is nothing but what did we save? Combined X, right? Again, being paranoid. Combined X equals to my image. Is it .all? I rarely do these. Yeah, it's all trues, as you can see. It's telling me yes, of course, it is same as this image. Yeah, at every pixel position. Again, a sanity check. Now I'm happy. Now test mask. My test mask right here is 128 by 128 by 128 with 4 classes, 0, 1, 2, 3. So let me convert that to categorical. Test_mask. Now you can see it's 128, 128, 128 by 4. So it's converted to categorical. So this gives you a nice idea of what we are going to do now to all of our images. Okay, so end of understanding the dataset. Now get organized. Okay, so what do we do? First of all, let's define our T2 image list, T1 CE, FLAIR, and mask list. We are ignoring T1. These are the ones we care about. We are going to combine these 3 images into a single volume, and we are going to convert my masks into categorical. But this is just a list, right? I'm using glob.glob. Okay, so let's go ahead and first get the T2 list so you get a good idea of what we are talking about. T2 list is nothing but our file names. Okay, how many should we have? 369, right? So let's do this, 368, 0 to 368, so 369 files. Okay, so this is where I was going mad. When I looked at masks, I only saw 367 or something. I'm like, what's going on? So anyway, change the file name in folder number 355. Okay, let's go ahead and define all of these. And once we have this, now we can walk through each image, right? How are we going to do this? So for my each image, in the range of how many ever the length of T2 list is, which is, we know that we have 369 images, do this following tasks. What tasks? First of all, my temp image T2 is use the Unlabeled library to load that image. So we have a NumPy array and then scalar fit transform. Exactly the same step we done earlier. Instead of one image, we are doing it for multiple. So we are doing exactly the same. Load T1 CE, load FLAIR, and then for each of these, go ahead and apply min-max scalar. So we'll get those. And then for the mask, we know what we have done earlier, right? We converted that into a NumPy array, into unsigned integer 8, and then changed all values of 4 to 3. That's it. Once you do that, okay, after you do that, go ahead and temp combined images. We are going to stack my FLAIR, T1 CE, and T2 together along the axis 3. And then we are going to crop them into size 128 by 128 by 128. Basically, this is nothing new. We just did that earlier. So we are just putting this in a for loop for each image. And then this is a new step here. Look at val and counts in np.unique. We saw np.unique earlier. What does that return? It returns us the unique values in the array, which should be 0, 1, 2, 3 in our mask. And then it also returns the number of counts, number of values, number of these values, the counts of these values, meaning how many zeros do you have, how many ones do you have, and so on. Why are we doing this? Because if I look at a volume, if that volume has less than 1% of mask, I'm not going to use it. It's a waste of my computing resources. That's exactly why I'm extracting this. And then if the value 1 minus this is greater than 0.01, or you can just say if this is less than 0.99 or something, then save. First of all, convert the mask to categorical, okay? And then save the 3-channel image or volume and also the mask as NumPy arrays into my folder called, now let's go in here. Where did I save it? Input data 3 channels, images, and masks. So it saved these as NPy. Okay, so how many do I have? I have 344. Out of 369 volumes, 344 seem to be useful, or 344 have a segmented volume greater than 1%. That's what that means. Okay, so this part does that job. Now that you have images and masks right here, we need to separate that into, split that into a training and testing. Now, you could ask, why am I doing this? Because I already have a validation data folder right there. That's a good question. I recommend you to just use the entire training and do exactly the same exercise for validation. That way you have 344 for training, volume for training, and then you have much more volume right here, 127 or so for testing purposes, for validation purposes. So I chose to only work with training data here because I wanted to look at the results in a fast way. But in real life, you should be using both of these, okay? So this step is optional depending upon how you're doing your things. But eventually, what I have here is BraTS2020 training data folder. And within here, I have input data 128 with train images, all NumPy arrays, train masks, all NumPy arrays, and validation, same thing, images and masks. Okay, here I have 86 images, and for training I have 258 NumPy arrays. Okay, so that's a lot, but I hope it gives you a good familiarity with the data set. Again, now you understand why I'm dividing this into multiple videos, because we want to focus one thing at a time and slowly get to our goal. Okay, again, quick summary is NII images, find a way to load them, which is using Unlabeled library. Once you load them, go ahead and normalize them or scale them to values between 0 to 1, or however you would like to normalize it. Combine the channels of interest into one single volume so it's easy for you to train them later on. And I chose to combine FLAIR, T1CE, and T2. And for the mask, I converted them into categorical after changing my mask pixel value 4 to 3. That's all we have done. Half an hour video, but we just learned how to handle this. In the next video, let's, which I promise to be to keep it a bit short, let's learn how to define a custom data generator where we can not randomly, but load a batch of 16 images at a time for training. Okay, thank you guys again for being patient in watching these videos, and if you like them, hit the like button. Again, please do subscribe to this channel. Thank you.